Good evening everyone. Welcome to the week 3 live interaction session for the course Colloids and Surfaces. Let's just wait for a few minutes for others to join before we begin our session for today. So let's just start our session for today. Let me just share my screen. So I hope my presentation is visible to everyone and I'm audible also at the same time. Let me just check whether the recording is going on. Okay. So yeah, let's just go ahead with today's session. Good evening everyone. Welcome to the week 3 live interaction session for the course Colloids and Surfaces offered by Professor Basavraj from the Department of Chemical Engineering under the NPTEL program. I myself Pratyumnan, one of the course team members responsible for conducting the live interaction session. I am a PhD scholar at the Department of Chemical Engineering, IIT Guwahati. So in the last 2 weeks of live interaction session, we focused on understanding the fundamentals of what is a colloidal system, the definition of the colloidal system, and then we went on towards characterizing the colloidal particles. We also discussed the classification of the colloidal particles, like based on the type of dispersed phase and the dispersed medium, and then we saw the classification of colloid based on the nature of the colloids, such as the lyophilic and lyophobic colloid, and then the third one was based on the where we saw about the multimolecular, macromolecular and associated colloids. So after that we went through the characterization, where we focused on understanding the different shape, size, density of the colloidal particles, and then we focused on two parameters. One was the surface charge density and another one was the grafting density. Then we discussed about the different type of forces acting on the colloidal system, and then the type of interactions on the colloidal systems, followed by we solved several problems for both week 1 and week 2 lecture. So in this week 3 lecture we will be focusing on the interactions that exist between the colloidal system. So as we discussed in the week 2 live interaction session, we just briefly discussed about the 4 different type of interactions that can exist between the colloidal particles. So can anyone tell me what are the 4 different type of interactions that exist in the colloidal system? Yes, anyone? We discussed about 4 different type of interactions, if you remember. Hello? Any ideas? We discussed about 4 different type of forces as well as 4 different type of interactions also, but it's just that we just didn't really discuss in depth. We just we just listed the different type of forces. Any idea? So the 4 different type of interactions that exist in the colloidal system are: one is the hydrodynamic interactions, depletion forces, surface interactions, and then the last one was the vanderwaals interactions. So that vanderwaals forces of interaction was the last interaction that we discussed about, and it is actually one of the most important type of interactions in the systems as well. So this week's course and today's live interaction session will also be focused on the different type of interactions, or specifically the vanderwaals interactions that is present between the colloidal particles in the system. So okay, let's just go to this let's just discuss about the week 3 topics before we come here. So let's just leave this question for aside now. Yeah, so van der Waals forces of attraction. So these are some, like, when two particles actually interact with each other, there will be a number of different forces that will be present between them, or that will be acting between them. So one is like sort of that electrostatic interactions. So when two particles of opposite nature, when they come together, or when two particles of similar nature or similar charges also come together, they will have, or they will experience some sort of an electrostatic interactions. It could be either repulsion or attractions as well, because if you bring particles which have the same polarity, like which has the same charge, they will repel each other. But at the same time, if one has a positive charge and then the other one has a negative charge, they will try to attract each other. So that is one form of interaction, which is the electrostatic. The next one is the van der Waals forces of interactions. So this van der Waals forces of interactions are nothing but specifically the attraction forces that exist between the molecules in the system. And since this course is specifically on the colloidal particles, we will say that the van der Waals forces of attraction exist or is acting on the two particles of a particular colloidal system, or two colloidal particles. So this van der Waals forces of attraction basically consist of three components. One is the Debye interaction, another one is the Keesohm interaction, and then the third one is the London dispersion force, or you can also call it as London dispersion interactions. So these interactions exist between two molecules or two colloidal particles, but then it is not like they exist between every molecule that is present in a particular system. So they have some specifications. So since this was already discussed in the course also by professor, so can anyone tell me what could be the combination, or this Debye interaction exists between what two different type of molecules? This is very simple, it was discussed in the course also. So the Debye interactions exist between these two type of molecules. Keystone interactions also similar, and London dispersion also, it is like it exists between two different type of systems of molecules. Any idea? Yes, any idea on where these interactions could exist, or like between what type of molecules these interactions can be present? So it is simple, right? So like if you see the very first lecture for the week 3, you can also see there this particular information. You could actually get this idea from there also. So Debye interactions actually exist between a permanent dipole and a induced dipole. Keystone interactions will exist between two molecules which has a permanent dipole moment. And your London dispersion forces will exist between two molecules that have induced dipole moment. Induced dipole and induced dipole. So here we encountered terms. Here we encounter terms such as excuse me, dipole moment, permanent dipole, induced dipole. So what are these? So these are like, so a dipole is nothing but when two positive charges are basically separated by a distance of L, then that system is called as a dipole. And then so yeah, that is what is a dipole. A dipole is nothing but when you have a positive charge and a negative charge of equal magnitude, and when they are separated by a distance of, let's say, L, then this system is called as a dipole. So there is something called permanent dipole and there is something called as an induced dipole. So permanent dipole is nothing but it's like that is something that is inherent to the system or exists within a system. So for example, permanent dipole exists in molecules like water, HCl, then you can have some sort of like polar compounds basically. So over there if you see HF is also one good example, I mean very good example compared to HCl. So over there the reason for it having a permanent dipole is basically because of the difference in the electronegativity of the element in the system. So if you take H2O or HF or HCl, if you take the elements apart from the hydrogen, that is your oxygen, fluorine or your chlorine, they are more electronegative compared to that of your hydrogen. So since they are more electronegative, they have a tendency to attract the electron towards them. So that basically results in a two charges of opposite nature getting separated by a certain distance. So they have a dipole moment. So that dipole moment that is inherently present in the molecule due to the electronegative difference of the elements is called as a, or they said to exhibit a permanent dipole, or that system is called as a permanent dipole. Whereas in case of an induced dipole, what happens is, let's say for example you take a neutral atom, and then let's say there is another one molecule which has a permanent dipole moment. Due to the interactions between this molecule with a permanent dipole moment, there will be a sort of a distortion in the electron cloud around the nucleus. So when that happens, we say that the dipole moment is induced in the molecule, or this inducing of dipole could also happen because of the disturbances that can happen in the electronic cloud around the nucleus. So it's just that the electronic cloud around the nucleus gets distorted. So that is called as an induced so that is an induced dipole. So that's how these three interactions are classified. So a permanent dipole is nothing but it will inherently have a dipole moment for itself because of the electronegativity differences in the elements present in that particular molecule. Whereas in case of an induced dipole, those type of molecules do not have any dipole moment for themselves, and due to the interactions or some sort of electronic disturbances, they will get a dipole, or a dipole gets induced in these molecules. So based on this permanent dipole and induced dipole interactions, we have three different types of them, three different types of interaction. One is the Debye, so it is between a permanent dipole and an induced dipole. So that example that I gave, so you take a neutral atom and then a permanent dipole is interacting with this neutral atom. Due to this dipole moment, it induces a dipole in this neutral atom or the molecule. So this interaction is called Debye interactions. And another one is called keystone interactions, which is the interactions between two permanent molecules, two molecules with permanent dipole moment. The third one is the London dispersion forces. So these forces are nothing but they have induced dipole, and both the molecules that are interacting have an induced dipole in their system. So this is called as the London dispersion forces. And then if you see the chart where there are different type of elements, let's say for example different type of compounds, like for example if you see in this question number 2, you have thiophene and fluorobenzene, right? So apart from that, if you see in the course also, there is a list of compounds for which we have the percentage of Debye interaction, keystone interactions, and then the London dispersion forces. So how much each type of interactions contribute to the van der Waals forces of interaction, that chart is given in the lecture if you see. So over there if you see, in all the molecules this London dispersion forces will exist, and it is not mandatory for the Debye or the keystone interactions to exist, but in majority of the molecules which do not have dipole moment, or in majority of the non-polar molecules, the London dispersion forces contribution to the van der Waals forces of interaction will be very high, because they do not have a dipole moment, right? So they cannot induce a dipole or interact with the another molecule. So they need an induced dipole within them to contribute to the van der Waals forces of attraction. So non-polar molecules do not have a permanent dipole moment, and that is the reason in that particular cases of non-polar molecules or molecules which does not have a dipole moment or a symmetric molecules, there the London dispersion forces will be greater. So yeah, we were here. So this is how you can write the expression for each of them. let me just so this so the potential energy for this particular type of interactions are usually represented by a symbol phi. So the phi is given as the sum of all the three types of interactions. One is the Debye, another one is the Keystone, another one is the London. So the sum of all these interactions makes up the van der Waals forces of attraction. So can anyone tell me what could be the so which component is for what type of interactions? I have given 1, 2, 3. So can anyone tell me which one belongs to Debye, which one belongs to Keystone, and which one belongs to London dispersion forces? I'll just put it in a presentation mode. Yes, anyone? Well, among the three, or like which particular interactions is does these three represent? 1, 2, and 3. Anyone? Yes, I mean this was given in the course also. So it's just that the expression, you need to tell me which expression among 1, 2, and 3 represents the Debye, Keystone, and the London dispersion forces. Anyone? Yes. So since I didn't receive any answer, so let me just mention this. But you should always try to, like, if not memorize the entire expression, but at least you should be able to identify which one belongs to which type of interactions. So that will be helpful. So yeah, the first one belongs to the Debye interactions, and then the second one goes for the Keystone interactions, and then the third one goes to the London dispersion forces. So, or you can say London dispersion or London interactions also. So this is the entire expression. The first one is for Debye, second one is for Keystone, and then the third one is for your London dispersion forces. So yeah, let me just explain the variables also. So if you see for the Debye interactions, or if you see the entire van der Waals forces of interactions, there are two things that is common. One is this 4 pi epsilon the whole square, and another one is the x power 6. So this states that all the and another one is the negative sign. So the negative sign represents for the attraction forces, and the positive sign is given for the repulsive forces. So with this sign convention, we can state that the van der Waals forces of attraction that exist in any two type of molecule or any two type of the colloidal particles are always attractive in nature. So that is one. And then the second one is what you can see is the van der Waals forces of attraction or van der Waals forces of interaction is inversely proportional to the distance between the two molecules raised to the power 6. So you can see the order in which the van der Waals forces of attraction will vary with the distance between the two molecules. So if you bring the molecules very close to each other, then the van der Waals forces of attraction will be very high. But if you take it far away from each other, then the value of phi will decrease because it won't be able to interact with each other. So, and after a particular certain distance, there will be no type of interactions between them. They will act like an individual atom without any neighboring effect. They will be like in an isolated state, so without interaction from any of its neighbor. So yes, so it varies with the distance between the molecules, and that is raised to the power 6. So here I would like to add one more point. In case of the molecules or the atoms, if you see, the interactions between two molecules will disappear, or they will stop interacting with each other, or they will stop interacting with each other when the distance between them goes beyond 0.8 nanometers. So if you see that Lennard-Jones potentials graph, where it is written energy, where it is shown, where you can see the variation of the energy with the separation distance between the two molecules. So if you see there, beyond 0.8 nanometer, you can see there is no interactions between them. So beyond that 0.8 nanometer limit, the two atoms or molecule will behave like an isolated atoms, or if two atoms are present, if their distance is more than 0.8 nanometer, they will behave like a isolated atom. But in case of colloidal particle, the system is the range is different. So can you tell me what could be the range for a colloidal system? It's not 0.8. It's in the the interactions between the colloidal particles are like in the long range order. Anyone? So it is between 0.2 to 10 nanometers. So even if you separate two colloidal particles, up till 10 nanometer ranges, or till 10 nanometer range, if you separate them, then also there will be interactions between the two colloidal particles. If it goes beyond 10 nanometer, then there might not be, or the interactions between them might be so negligible that you can consider them as isolated particles. So this the order or the separation distance range increases in case of a colloidal particle compared to that of the atoms or molecules. So can you tell me why this happens? Like, why in case of an atom it is 0.8 nanometers, whereas in case of the colloidal particle the interactions goes in the long range order? Any idea why? Oh, sorry. Any idea why does the so when two colloidal particles are able to interact with with such long range order, when even when their separation distances is greater compared to compared to that in the case of atoms or molecules, which means that the strength of the interactions between the colloidal particles is more compared to the strength of the van der Waals interactions between two atoms or molecules, right? So because of the increase in the strength only, even though the colloidal particles are separated up to a greater distance like 10 nanometers, they are still able to interact, whereas that is not possible in case of your atoms or molecules that you take. So can you explain why that the strength of the van der Waals forces of interaction in case of the colloidal particles is greater than that in case of the atoms and molecules? So any thoughts on why? The logic is very simple. I like to hear it from you people, like why. I mean, for a colloidal particle the strength is more, the strength of van der Waals forces of attraction is more compared to in case of your atoms and molecules. It is very simple. So the main reason is because the colloidal particles that you take have a large number of atoms or large number of molecules. So over there you are considering only two entities, two atoms or two molecules. Here the colloidal particle consists of a lot of molecules, right? So because of having a larger number of molecules within them, they have more strength of interactions compared to the atoms or the molecules. Because the colloidal particles has a larger number of atoms, the strength of their van der Waals forces of attraction is more, and that is the reason they are able to interact with each other even though when they are separated to a distance, to a larger distance like 10 nanometers. So yes, that's it about this equation. So let's just concentrate on what are the parameters that is there. So we have alpha, mu, and then we have epsilon, and then we have nu, and then we have h. So let's just write down what each of this each of these variables represents. So I would like to hear it from you guys again. What could be the which variable signifies what. So anyway, so first is mu. So mu represents for the dipole moment. So which can be written as, anyone knows what is the expression for the dipole moment? It is qd. So q is the charge and d is your distance between the two charges, right? So q so we told that the dipole is nothing but when two charges of equal magnitude but opposite in polarity, when they are separated by a distance d, then that system is called as a dipole. So dipole moment is mu equals to q, that is the magnitude of the charge, times the d, that is the distance between the two charges. And then next we have is the so in this expression we have something called as alpha. So alpha is nothing but, it is called as the polarizability. So what do you mean by polarizability? So it is basically the ability to induce a dipole moment in a molecule. So you have a neutral atom, and then you are going to um, induce a dipole moment in this neutral atom, either by using a permanent dipole or by electric field. So that ability to induce a dipole moment in the molecule is called as polarizability, and the molecule that where the dipole gets induced is said to be polarized. So yeah, so basically, upon placing a neutral atom in an electric field or by using a permanent dipole, you basically distort the electron cloud of an atom, and you induce a dipole in that system, in that neutral system. So that particular ability is called as polarizability of a molecule or of a system. And then you have Kb. So Kb, wait, let me just expand this. So Kb, again, it is the Boltzmann's constant. We have been discussing this for the last 2 sessions also. Please remember the value of Kb, 1.38 into 10 to the power minus 23 joule per Kelvin. And then you have nu. So nu represents for the frequency of the vibrations, and h is nothing but it is the Planck's constant. So anyone know the value of Planck's constant? Planck's constant, h. What is the value of h, Planck's constant? Yes, h, that you guys know what is the value of h. Yes, it is 6.636 into 10 to the power minus 34, and what is the units? Joule second. Yes. So this is the value of Planck. So these are the different type of physical different variables in your expression for the potential energy or the vanderwaals forces of attraction. The potential energy, for the vanderwaals forces of attraction. So yes, let's just move towards the next slide. So what we have discussed so far is something that is related to very microscopic entities. So it is between 2 atoms or 2 colloidal particles that is there in which is in the nanometer or the micrometer ranges basically. Now we use this van der Waals forces of attractions, and then we try to scale it up for the macroscopic objects, like again, when I say macroscopic objects, they are also within this nanometer ranges only. So we try to scale them up from this atomic. So we basically discuss the van der Waals forces of attraction for atoms and molecules, right? So we try to level that up or scale that up for the macroscopic objects. So here you can see 2 different expressions. So again, the derivation is there within the lecture. So this live interaction is supposed to be only for problem solving. So for the derivation, I would suggest all of you to go through the lecture. Over there you will be able to understand how did we arrive at these formulas. So they are specifically derived in the video lecture, so please go through that. I'll just explain the terms that are present here. So yes, so between 2 spherical colloidal particles, the general expression is minus half rho Na by m the whole square beta double integral r power minus 6 dv1 dv2. So what is this beta? So this beta is nothing but, so if in this expression, if you see, if you group all of them together and then remove the common terms alone, you will be left out, let's say if you just group out the terms that are common. So if you just remove this 4 pi epsilon, if you just take this 4 pi epsilon naught square and x power 6 as common, whatever the portion of the equation that you are left with, that you can represent it as beta. So that is beta. Yeah, I can write the expression for beta. So just a second. Yeah. So beta is so so beta is nothing but it's equal to let me just yeah, it is alpha 1 u1, that is your dipole moment, whole square, plus alpha 2 u2, that is your dipole moment the whole square, plus you have 2 by 3 times of, let's just see what is it, mu1 mu2 square by kbt. So u1 u2 and both of them are squared by kbt, plus then you have the last one which is this expression. So it is like 3h by 2 3h by 2 v1 v2 nu, I mean this is nu1 nu2 by, oh sorry, nu1 plus nu2 by nu1 nu2 times alpha 1 alpha 2. Yes. So this is your expression for beta. So the common terms will remain, that is your 4 pi epsilon naught square and x power 6, but apart from that, what is the value of, so this particular terms that is that is remaining can be expressed as beta. So this is beta. Then rho is nothing but the density, m is the molecular weight of the the colloidal particle that you are taking or of the system that you are considering, Na is the number of atoms, and then you have this v1 v2 r power minus 6. So that is like one particular sphere and another sphere when they are separated by a distance of r. So that is what is the meaning of this expression. So if you see, if you take, let's say, two particles, okay, so one and then 2, and then let's say that they are separated by a distance of, let's say that you have system 1 with particles A and B, and let's say that the radius of the particle is 20, and radius of both the particles Ra and Rb are 20 nanometers, or let's say 200 nanometers, and they are separated by a distance R, which is, let's say, 20 nanometers. Then we have a system 2 of particles C and D. Let's say Rc and Rd are of diameter 10 nanometers, and let's say they are separated by a distance of R, which is 1 nanometer. Then the interactions, and here we should take that both AB, CD, if they are of same composition, and if their radii as well as the distance separated, or the distance of separation between them are, are like in a kind of a scaling factor, then the van der Waals forces of attraction between both the systems will be the same. So if you consider a system of particles of the same chemical composition or of the same composition, and if their radii and the separation distance are are in the same order or as like a scaling factor, then the van der Waals forces of interactions or the potential energy for these interactions will be the same. So this is about two spherical colloidal particles, and this is more of a generalized expression. You need to integrate this. Now we come to what is the expression in case if it is a two semi-infinite blocks. So in that case the expression will be minus rho Na by m the whole square times pi times beta times 1 by 12 z square. So here the z is nothing but is the separation distance or distance of separation between the two infinite blocks. Z is the separation, or let me write as distance of separation between two blocks. So this term, if you see that rho Na, so again if you see everywhere we have a negative sign, so which again and again it indicates that these potential these forces that exist between the molecule are attractive in nature. So the expression, if you see the rho Na by m or rho NaM pi the whole square is called as the times beta. This expression, if you see this one is can be represented, this is something that is common for every kind of system that you take, either if you take your general expression or spherical or the semi infinite blocks or any type of other system for which the expression is derived, like parallel cylinders or between a sphere and a flat surface. Everywhere this term rho Na pi by m the whole square times beta will be the same or will be in common. So for that reason we call this expression as Hammaker's constant or Hammaker constant, and this has a lot of importance within the colloids and interfaces or surfaces. So this expression is very important, and I would like you to also go through and check what could be the physical significance of this Hammaker constant, and we will discuss this in the next live interaction session also about more in detail about this Hammaker constant. So this is about today's kind of summary of what is there in the live 3 of what is there in the you know uh, the video lectures for the week 3 or the course for week 3. Now let's move on towards solving some problems. So again, this is very important. We have almost around like 6 questions to solve for today. So yeah, let's just go one by one, and I hope you guys also solve with me parallelly, so that that is the main motive of this session, so that you get the practice to solve. So it is written, so the question is, calculate the van der Waals energy of interactions for the two molecules given below, and then they are asking you to calculate the individual the value for individual interaction, that is your Debye, Keystone and London dispersion forces, and then their contribution to the total van der Waals forces of attraction, like each contribution to that van der Waals forces. So I mean, this is a very straightforward question, right? So just take some of your time to solve it, and then I'll also solve here. It's simple, you just need to use the formulas that is given to you. Yeah, but one thing that I would like to say is that here if you see, you have mu2 mu1, that is because we consider because in this expression the two atoms or two molecules or two system of interest are dissimilar in nature, but here you can take them as same, like thiophene, two molecules are interacting with each other, and then you need to calculate the expression for them. So it's like two problems for two different molecules, same problem but for two different molecules. So you know this expression will get reduced, since it's both are thiophene molecules. This alpha mu2 and then this alpha 2 mu1 whole square, both of these will be the same, so you can write this as 2 alpha mu square. Similarly, this will become mu whole power 4. This again, this will become alpha square, and nu1 plus nu2 will be 2 nu1 by nu1 square, so that will be 2 by nu1. So you can reduce this expression accordingly to solve the problem. So let me just write what will be the expression for the Debye. So Debye interactions in that case will be, let's just keep that 1 by 4 pi epsilon the whole square times x power 6 to the n, and then just focus only on the other parameters. So it will be okay, just a minute, one data is missing. So yeah, here consider the distance of separation x as 10 nanometers. Now, then I think it will be complete. So it will be, so here since both are thiophene molecules, alpha 1 mu1 square plus alpha 1 mu2 square plus alpha 2 mu1 square will become alpha 1 mu1 square, right? 2 times of alpha 1 mu1 square. So 2 times of alpha times u1 square, this divided by, you have your 4 pi epsilon epsilon whole square times x power 6. So what will be the expression? So here your mu is given in debye. So how much? So you need to actually convert that debye unit to SI unit. So how much is 1 debye? Yes. How much? I mean, what is the SI unit of debye and what is the conversion factor? So 1 debye is 3.35 sorry 3.335 into 10 to the power minus 30 coulomb meter. So please keep this in mind. I mean, this will be given to you in the question, because if you see the assignment question also, over there it is given what is the unit of conversion for debye and what is the value of epsilon. So you can take it as 2 times mu1 square, so that will be 0.51 times 3.335 into 10 to the power minus 30 the whole square. Oh, so there are a lot of chances that you can do mistakes in calculation, so please be very careful when you solve, because there are a lot of parameters with in the order of 10 power minus 30 and then whole squaring that, so it will be quite confusing, so please be careful. This times your alpha. So here if you see, the units of alpha is given as alpha by 4 pi epsilon into 10 power 30 is 9.76, right? So which means alpha by 4 pi epsilon is equal to 9.76 into 10 to the power minus 30. So you have to be careful there. Let me just write this. Alpha by 4 times 4 pi epsilon is into 10 to the power 30 is equal to 9.76. So this 10 power 30 will go to the other side, so the value of alpha as such is 9.76 times 10 to the power minus 30 times 4 pi epsilon. So this is your value of alpha. So this has been given in the question, represented in the question this way, so that it is actually easy for the representation. So whenever the you have like alpha by 4 pi epsilon into 10 power 30. Here also if you see, it is written beta into 10 to the power 77 as 3.90. So this means the value of beta is 3.90 into 10 to the power minus 77. So you need to take the units to the other side. Yeah, so that's about here. So here if you see, I'll make a small modification so that the terms, the values gets much easier to handle. So here if you see, it is written alpha and you have 4 pi epsilon the whole square right here, and here you have alpha by 4 pi epsilon. So I will take that expression outside the column, so that will be 9.76 times 10 to the power minus 30, right? So please solve parallelly, because this is a kind of it is very easy to make mistakes. So yeah, divided by, so since you have taken 1 4 pi epsilon the with this alpha, you just have only 1 4 pi epsilon at the bottom. So it's not 4 pi epsilon square, it's just 4 pi epsilon. And what is the value of epsilon? Anyone? Epsilon, that is 8.85 times 10 to the power minus 12, right? This times x power 6, and x is given as 10 nanometer. So 10 nanometer, when you convert it into SI units meter, it is 10 into 10 to the power minus 9. So that will be 10 to the power minus 8. Whole power 6. So you can see how many powers and this expression has. So that's the reason it is better to be careful when you do that. So if you calculate this, I mean, has anybody calculated the value? If yes, please let me know. I mean, I'm also prone to make mistakes here because of the lots of calculations. So if you find any mistakes, then please let me know. So here if you see, let's take the calculator, or in case if you don't understand also, then please let me know, so that we can see what can be done. So let's just deal with the square term. So it is written 0.51 times 3.335, okay, that whole square, 2.89289. So let me just write this, 2 times 2.2898 times 9.76, and here you have 10 power minus 30 the whole square, so that will become 10 power minus 60, and here you have 10 power minus 30. So here you have 10 power minus 30, when you square that, it will become 10 power minus 60, and here you have 10 power minus 30. So that will become 10 to the power minus 90. right, divided by, coming to the denominator, let's just multiply the ones without the power. 4 times 3.14 times 8.85, 111.156, 111.156 times, you have 10 power minus 12, and here you have 10 power minus 8 the whole power 6. So 10 power minus 8 the whole power 6 will be 10 power minus 48. So you have 10 power minus 48, you have 10 power minus 12, so that will become 10 power minus 60, right? So so I hope you are following what I am saying. So now just let's calculate the numerator term. 2 times 9.76 times 2.2898, so 44.696 divided by 111.156. whole to the power 10 power. So you have minus 90 in the numerator and minus 60 in the denominator. So when the minus 60 goes up, it will become 10 to the power minus 30. So that will be, so you have to divide this now. This divided by 111.156, 0.402. Point 402 times 10 to the power minus 30. So these many joules. So this is the amount of energy or the potential energy that comes from the Debye interactions. So similarly we have to do for Keystone and London dispersion interaction. So let's do that. I'll do for the thiophene molecule, you can do for the fluorobenzene molecule in your, like, as a home task you can take, because since this involves a lot of calculation, if we do for both the molecules today, we won't be able to cover up for the rest of the problems. So let me take this to the other slide. Let me put it here. So if you have any doubts, then please let me know so that we can solve, or if you are getting some other answer also, please let me know so that I can also see whether I have made mistakes anywhere. Again, it's a very clumsy calculation, so please be careful with your digits, variable, with substitution of the variables, the values for the variables, the unit conversion. Next we have the Keystone interactions. So what will be the formula for Keystone interaction? Keystone interaction will be 2/3 times mu1 mu2 whole square, but here both the molecules are same, so it will be u1 power 4, mu1 power 4. I will write it this way, 2 times mu1 power 4 divided by 3 times kBT. So this will be quite simpler calculation. So keystone interaction is equal to 2 times u1. So u1 is 0.51 times 3.335 times 10 to the power minus 30. Again, this is for the value of mu, and this one, since it's in debye units, I am converting it to SI units. This entirely whole power 4 divided by 3 times kBT. K is Boltzmann's constant. So what is the value of Boltzmann's constant? I said just a few minutes before. What is the value of Kb? I mean Boltzmann's constant. 1.38 and then 10 power minus 23, right? Times T. Since T is not given in the question, let us assume it as 298 Kelvin and then solve. So what is the value for this? This calculation is not as big as what we did for debye. So I think you will be able to tell me. So let's calculate. Please you also calculate together with me and let me know what's your answer as well. 0.5 into 3.335 into 10 to the power minus 30, right? Wait just a second. 0.51 times 3.335 times 10 to the power minus 30. Yeah. No, let me calculate once again. Oh, okay, sorry. So just let us keep till this expression. So 0.51 times 3.335, 1.7. So 2 times 1.700 or 7 times 10 to the power minus 30 whole power 4 I don't know why this keeps repeating. Okay, anyway, divided by this same, I'll just write it as 3 kBT for the time being. So this value will be so 1.7 whole power 4, right? 8.368 times 10 to the power minus 120, because minus 30 times 4, so that will be minus 120 times 2 divided by 3, so that will be, so times 2, so this, okay, let me just write that expression, right? 3 times kBT, so that value will be three times 1.38 times 298, 1233.72, 10 to the power minus 23. So this expression is nothing but 8.368 times 2, that will be 8.368 times 2, 16.736 divided by 1233.72, or you can write it as 1.233, and this will be in 10 power minus 20. So since we made 1233.72 into 10 power minus 23 as 1.233, so the power will be 10 power minus 20. So in the numerator you have minus 120, in the denominator you have minus 20, so that will be minus 100. So what is 16.736 divided by 1.233? 13.573 to 10 to the power minus 100 joules. So this is for the keystone interactions, and that is for the Debye interactions. Now let's calculate what is London dispersion force contribution. I hope you also got the same values for this Debye and keystone. If you have calculated some other value, then please let me know. By the time I'll just write the formula. So it will be 3h times alpha square new. So let me check whether I wrote it correctly. So yeah, okay. Oh, see, we made a mistake. In the keystone interactions, we did not bother to multiply that 4 pi epsilon the whole square times x power 6. So we are supposed to multiply that. So that will be let me just take this. So we did not consider this expression that was there. So this is the thing that can happen. That's the reason it's better to solve and then verify that once again. So this will be divided by just let me take it as a separate one. Divided by 4 pi, that is 3.14, epsilon is 8.85 into 10 to the power minus 12, and this is squared, so a whole square, times you have your x power minus 6, so 10 to the power 10 nanometers, so 10 power minus 8 the whole power 6, so that is 10 power minus 48. So what will be this expression? So it is 4 into 3.14 times 8.85, 111.156 whole square, 12355.65. Let me just take this up. So what was the value? 12355.656. So here you have 10 power minus 12 the whole square, so that will be 10 power minus 24, and you have 10 power minus 48, so that will be 10 power minus 74, right? oh sorry, 72. So now what will be the expression? So this you can write it as 1.235 times 10 power minus 68. So if you take this 13.573 divided by 1.2355, that is 10.98 times 10 to the power, so minus 100 minus 68, so that will become plus 68, so minus 100 plus 68 is minus 32 joules. So this is the keystone interactions. So that is the reason it's better to be careful, because here we forgot about the term 4 pi epsilon the whole square times x power 6. So be careful. Yeah. So let's go to London dispersion forces. So here this V1 plus V2 by V1 V2, or nu1 plus nu2 plus by nu1 nu2. So since it is same, the numerator will become 2 nu1 and denominator will become nu1 square. So that nu1 and nu1 square will get cancelled, and this will become 2 by 3h by nu1. This will become alpha square. This times you have again your 4 pi epsilon whole square times x power 6, right? So you just need to calculate this. So this will be let me take this expression to the next slide so that it will be easy. So that it looks ordered. So for the London dispersion forces, so 3 times h is 6.636 times 10 to the power minus 34 times. So here you have alpha square and you have 4 pi epsilon the whole square at the bottom. So I can take it as alpha by 4 pi epsilon the whole square, and since I know the value of alpha by 4 pi epsilon as where is it? So since I know the value of alpha by 4 pi epsilon as 9.76 into 10 to the power minus 30, I can just substitute that and square it. So 9.76 times 10 to the power minus 30 whole square so I think divided by the what is that, x power 6. So that will be 10 to the power minus 48. So let's just do the multiplication. So that will be 3 into 6.636 times 9.76 the whole square (95.2576), right, times 10 to the power minus 30 whole square. So that will be minus 60 minus 34. So minus 60 plus minus 34 will be minus 94. Right, 10 to the power minus 48. So when that comes up, So minus 94 plus 48, right? So that will be around 46. Yes. Yeah. So what is the x value for this? Can anyone let me know? So this will be 3 times 6.636 times 95.2576, 106 1896.38 times 10 to the power minus 48 joules. Oh, this should be minus 46. Oh, oh, look at here. We made again, there is another one place where we forgot to consider one term. In the denominator, we forgot to use the term V, that is the frequency of the vibrations. Uh, so you can assume the frequency to be, let's say for practice purpose, we can take the what do you say, frequency to be so just a second. So assume the frequency to be 3 into 10 to the power 15 hertz. Sorry, 15. So which means this will get divided by 3, and this minus 46 plus 15 will be 29, right? And this will get divided by 3. Six 32.12, and you have, so that will be 6.32 into 10 to the power minus 27 joules. So this is your London dispersion force value, but you can see, so the reason why I told this is it's a simple substitution, but at the same time this will you are prone to make many mistakes here because of the larger number of variables, and then each variable having some 10 power minus some values in their as their exponent. So this will complicate the calculations, and it will take your time. So you can easily do mistakes. So please practice these kind of questions so that you get a good grasp on doing calculations much faster. So if you see here, compared to your let's check the exponents. So this is in the order of 10 power minus 30, your Debye interactions, and your keystone interaction is in the order of 10 power minus 32. But if you see your London dispersion forces, it's in the order of 10 power minus 27. So you can see that, in case of molecules like thiophene, the contribution of your London dispersion forces is greater compared to the other two, that is your Debye and keystone interactions. So now after this, it's very simple. You are just asked to calculate the total, so which is nothing but sum up of all the values, that is your van der Waals will be Debye plus keystone plus your London dispersion. So you can just add up. It will be in the order of 10 power minus 27 only, and then in order to find the contribution, so percentage contribution can be determined as, let's say for Debye it will be 0.402 into 10 to the power minus 30 divided by your total van der Waals, which I'm leaving it to you to calculate, times 100. Similarly, you can calculate for percentage of keystone also. So that will be 10.98 or divided by this total van der Waals into 100, and then your percentage of London will also be like 6.32 into 10 to the power minus 27 divided by your total van der Waals, the energy that you get for the total van der Waal after addition, that multiplied by 100 will give you the answer. So this is about calculating each individual forces and then finding out the contribution of each of them towards the total interactions. So now let's go to this question. So this is about the Lennard-Jones potential. So if you remember, we discussed about the separation distances being 0.8. So over there you will have this Lennard-Jones potential. So here the question states that the expression for the Lennard-Jones potential is given as phi equals to minus a by x power 6 plus b by x power 12. Value of a and b are 3.33 into 10 to the power minus 77 joule per meter per joule meter to the power 6, and and the b value is 9.5 into 10 to the power minus 34 joule meter 12. Joules per times meter whole raised to the power 12. They are asking you to calculate the Lennard-Jones potential at 6 nanometer separation, and then the next question is find out the separation distance at which the interaction potential energy will be minimum and state its value. So if you see the first question, that's very simple. It's straightforward substitution. You have a, you have x, you just need to substitute that value and get the value of phi. But how do you do the second one? Any thoughts on how to do the second one? Yes, any thoughts? So when they say a particular potential energy and when they ask you to find out the minimum value, what do you do? I mean, how do you mathematically approach this problem? Like, you are supposed to identify or you are supposed to calculate the interaction potential energy, but the minimum of it. Any idea? Yes. Mm, so you are saying that you will do, so it's like um, you do the, you take the derivative, so you are supposed to calculate the minima, right? So you take the derivative of phi and then you equate it to 0. So if you do that, you will be able to, so that will be the point where the potential energy will be minimum. So whenever, this is not just related to this question, whenever in any kind of problems that you get, if you are asked to calculate, if you are asked to what do you say, find the minima of a particular variable, then just take the derivative and then equate it to 0. So that is the way of solving it. And when you get and if you get two values, then you do double derivative of that particular expression and then find out whether that value is greater than 0 or less than 0. If it is, so depending upon that, you can identify whether that particular x that you have got before corresponds to minima or maxima. So let's just do for this question. So when you take derivative, so dou phi by dou times so dou phi by dou x is nothing but, so minus a, let me just write, d by dx of 1 by x power 6, x raised to the power 6. So yeah, plus b d by dx of 1 by x raised to the power 12, right? So you can write d phi by dx as minus a d by dx of x power minus 6. So 1 by x raised to the power will be x raised to the power minus 6, right? So plus d by dx of x raised to the power minus 12. So d phi by dx will be minus a, d by dx of x power minus 6 will be sorry, it will be minus 6 x raised to the power minus 7, right? It's like x square 2x. So I hope you can understand. So if you have x square, derivative of x square is 2x, right? So you bring the variable, so you bring the what is exponent to the front, and then the exponent that is there you subtract that with 1 plus b, it will be minus 12 x raised to the power minus 13, right? So this expression is equal to 0. Because we want to find the minima of that particular potential interaction potential energy. So if you just take this, so minus and minus will become plus in the side, so it will be 7, sorry, it will be 6a x raised to the power 6a by x power 7, or let me write it as 6a times x raised to the power minus 7. Just a second. B, sorry, 12b times x raised to the power minus 13. So if you see here, what you will be left out with is, so it will be like x power so this x power minus 7 and x power minus 13 you can cancel, so that will be like x power minus 6, or x, yeah, you just write it as like this, x power minus 6 is equal to 0.5 times a by b, or you can write this as x raised to the power 6 equals to 2 times of b by a. So what is 2 times of b by a? What is the value of b? B is 9.5 into 10 to the power minus 134, and a is 3.33 times 10 power minus 77. So 9.5 by 3.33 times 10 to the power minus 134 plus 77. So that will be 9.5 divided by 3.33, 2.85. So 2 times 2.85 times 10 to the power minus 134 plus 77 is 57, minus 57, right? Please calculate along with me, so that in case if there are any mistakes we can rectify those. So 2 times 2.85 is 5.7 times 10 to the power minus 57. This is x raised to the power 6. So x raised to the power 6 is 6 value is 5.7 into 10 to the power minus 57. So what is the value of x? X will be, so this whole power 1 by 6, right? So 5.7 into 10 to the power minus 57 whole power 1 by 6, right? So what will be the value? So for this I will use my personal calculator. If you are able to calculate, please let me know the value. So it is 5.7 into 10 to the power minus 57 whole power 1 by 6. So what value did you get? Yeah, so even I also got the same. So 4.2 into 10 to the power minus 10, or you can write it as 0.42 times 10 to the power minus 9 meters, or 0.42 nanometers. So this is the point at which you will be getting what do you say, the potential energy which will be maximum, which will be minimum. Now with this value we are supposed to calculate the minimum potential energy for this system. So let's just calculate that. I'll not be calculating for the first expression, because since we are doing the second one, it's just about substitution of the value. So it's like, let me first put the B value first. So 9.5 into 10 to the power minus 134 whole by divided by 4.2 into 10 to the power minus 10 whole power 12 minus 3.33 into 10 to the power minus 7 divided by 4.2 into 10 to the power minus 10 whole power 6. So what is the value? So 4.2 whole power 12, right? Let me just take this further ahead. So I hope you are able to understand. If not, please let me know. Oh, so this is 30129,469, or 3.01 into 10 to the power 7. So that will be so 9.5 divided by 3.01 times 10 to the power minus 134 plus 10 power minus 10, the whole power 12 will be 10 power minus 120, and when you take it to the numerator it will be plus 120 minus 7. So what we got by multiplying 4.2 the whole power 12 came out 3.01 into 10 to the power 7. If you take to the numerator it will become minus. This is one part of the expression. Next one you have is 3.33 divided by 4.2 whole power 6. 4.2, it is 5.489 into 10 power 3. So here you have minus 77. So minus 77 plus 60, because 10 power minus 10 whole power 6 will be 10 power minus 60. If you take it to the numerator it will be plus 60, and then the rest will be minus 3. So let me take this a bit beyond. So the value of 5 will be, so from here you have 9.5 by 3.01, that will be 3.15, okay, times 10 to the power minus 130, sorry, not 130. So this will be like minus 141 plus 120, so minus 21 plus minus 3.33 divided by 5.489, that will be 0.6, or it will be, you can take it as 6.06. So minus 80 and plus 60, so it will be minus 20 and minus 21, these many joules. So if you further simplify this, the value of phi will be so 3.15 and 6.06 minus 2.91 times 10 to the power minus 21 joules. So this is the interaction potential energy, the minimum interaction potential energy, and the negative sign that you see here, let me just, and then the negative sign that you see here basically represents for the, basically states that the interactions between the two molecules or between two atoms is attractive in nature. So the negative sign, yes, positive is for repulsion and negative is for attraction, is attractive in nature. So this is about this question. So you can always put for 6 nanometers, and then it's just about that you have to change the value of x power 6 and x power 12. But since we have done this question which is more extensive compared to the previous one, so I am not going to solve for that one. You can take it as a home task. So let's just do one question. So let's just solve the fourth question. They are asking you to calculate the Hammaker constant. So if you remember the formula, Hammaker constant is A equals to rho Na pi by m the whole square times beta. Here they have given your value of beta as 6.48 into 10 to the power minus 77. Rho is given, Na is given, and then they are asking you to calculate the Hammaker constant. So let's bring that expression here. Oh, sorry, wait. Oh. So A, please solve this. This is just about substitution, right? So you can solve this on your own and let me know the answer also. Meanwhile, I'll also solve. So density is 1.05 times Na, that is 10 to the power 25 times okay. So here, since the value of beta is in meter and density is given in centimeter cube, you need to change that to meter. So 1 gram per cc is equal to, or sorry, 1 kg per meter cube is equal to okay, 1 gram per cc is 1000 kg per meter cube, right? So it will be 1050, or you can write it as 1.05 into 1000 times. So please again be careful with the units. This is one way where you can actually get caught or like make mistakes, and then the value what you are going to get will be significantly different. You have Na, you have pi, so that is 3.14 divided by m. So here it is actually for aniline. Please take the molecule as aniline. Oh wait, no, this is for phenol. So take the molecule as phenol. So the molecular weight of phenol is, so formula for phenol is C6H5OH. So molecular mass will be 12 times 6 plus 5 times 1 plus O, that is 16, plus H1. This entirely whole square. So you need to see here again, you need to know the molecular formula for phenol. So please just remember, I hope it will be given in the question, but in case if you don't know, then I think it is, it is better to know at least the molecular weight of the components that is present in that chart. So if you see, there are so many, right? Water, aniline, chlorobenzene, fluorobenzene, ethanol. So at least know the molecular formula for them, so that it would be easy in case if the question comes out without the molecular weight. Times beta, that is 6.48 times 10 to the power minus 77. So has anybody calculated the value? Any answers? So let me just minimize this expression. So 12 times 6 is 72, plus 5 77, 78 and 94. That multiplied by this expression, 6.48 times 10 to the power minus 77. So value of A is nothing but, so 1050 by 3 multiplied by 1050 times 3.14 divided by 94, that is 35.07, 10 to the power 25, whole square times this 6.48 into 10 to the power minus 77. Did he calculate? Okay, I don't have the answer, so let's just check the answer. So it is 35.07 whole square, so 1229.9 times 10 power minus 25 whole square will be 10 power 25 whole square will be 10 power 50 times 6.48. So let me just write that 6.48 here. So it is 10 power 50 minus 77, right? Because you are multiplying. So the Hamakers constant will be 1229.9 times 6.48. So it is 7969.752 times 10 to the power minus 27. Minus 50 plus 50 minus 77, that will be minus 27, and it is 7.969 into 10 to the power minus 24. And what is the units of Hamakers constant? Yes, units of Hamakers constant. It is joules, right? Because kg per meter cube, number of moles per molecule divided by kg per mole. So and then that whole square, so you will be left out with the m power what do you say, m power minus 3 the whole square times joule by m power 6. so that will get cancelled, and then okay, let me just, but this is again given in the lecture, so you can do it. So it will be kg by meter cube times number of molecules per mole, that entirely divided by molecular weight, so that can be written as kg per mole or kg per kilomole, but it's just the unit, so it's just that the conversion factor times beta is j m power 6, j m whole raised to the power 6. So if you see this mole will get cancelled, kg will get cancelled, so you will be left out with just a second, yeah, a is nothing but 7.969 times 10 to the power minus 24. You will be left out with 1 by m cube times j m power, j m to raise to the power 6 . So this will be whole square, right? So m 1 by m cube whole square will be m power minus 6 times joule m power 6. So m power minus 6 and m power 6 together will get cancelled out. So what you will be left out is 7.969 times 10 power minus 24 units is joules. So the Hammocker's constant units is same as the units of the interaction potential, potential energy for the interactions. So this is about this question, it's just about substitution again. So we actually plan to do 2 more, but I think we are running, we have already taken extra time. So let's just do these 2 questions in the next live interaction session before we start our week 4 session, like before we start working on the topics for week 4. So if you have any doubts, then please let me know now. Yes, any doubts? Please use the Q&A forum also. So we have a forum Q&A, so you are always welcome to post any doubts. In case the assignment solutions has also been released, so if you have any doubts, then please use this 2-hour session to raise your doubts, so that we can solve it for you. And this interaction session's main focus or main motive is to make sure that you get some help for solving, or you get some help for these kind of doubts. Since it's an online course, we cannot interact with you much through that, just with the video lectures. So that is the reason there is a live interaction session. So if you have any doubts, then please let us know. Okay, so then let me just stop presenting. Okay, so let me just conclude the session for today. I like to thank everyone who were there in the meeting. So in case if you have any doubts, please let us know either through the Q&A forum, or you are also welcome to email me in the email ID that will be given in the in the PPTs that will be shared with you. Both the video recording as well as the PPT will be shared with you very soon. So the last week video will be shared with you positively by tomorrow. Actually, due to some technical glitch, the video recording did not come out properly, so that was re-recorded. So that will be published in the YouTube channel, as well as you will get an intimation. So please go through the video lectures as well as the live interaction session, and if you have any doubts, please let us know. So I like to thank, or take this as an opportunity to thank, Professor Basavraj and the NPTEL team for providing me this opportunity to interact with you all this Sunday evening from 5 p.m. to 7 p.m. The next live interaction session for week 4 will be held on 18th of August, Sunday, from same 5 p.m. to 7 p.m. So yeah, till then, keep learning, and thank you. Bye.